two pre-registrants for the challenge. The first is Brad and the second is Dr. Ting. Am I correct on that? No, okay, Dr. Ting occurs, and I'm sure Brad is Brad involved? Yes, good. Do we have any other volunteers to participate in the challenge? All right, I will go to my page to begin and give the challenge, then we'll go to the participants. So the challenge this month is to create a table that has 4 columns with the value for degrees, the value for radians, the value for the sign of a reference input, and the sign for computed input. The reference input is taken from some external source, table or some such, so you know correct values, and then the sign of the computed values are the ones you actually compute. And we say this is wide open. You can use inputs from any source you wish. The radians and sign computed are computed by the actual internal system. And you can use any representation, floating points, integers, and so on. And the little hook on this is that next month, we'll actually use this data table for another project. So we'll go back now to our participants, and let's go to Brad Nelson as number 1.
All right. Well, one immediate caveat, this either shows my low reading comprehension, or I think something went by about a change in the instructions, because I had the wrong number of entries in the table. So that with that, so I've already failed the challenge. But this is the approach that I took. So I used the sum trig identities. So you can take, sine A plus B, and there's a particular way to decompose a sine and a cosine into their constituent components. And you can, if you make the second value in that form a single degree, you can come up with a straightforward identity that describes an angle plus one's sine and cosine in terms of the angles, the prior degree back's angle plus 1. So I go through and use this particular identity to incrementally compute 180 degrees of the table. And then for the second half of the table, because the signs are the negation, I just do the negation that way. I suppose I could, strictly speaking, have done only 90 degrees, but I was lazy, and it was easier to just make the table longer than to flip it. I used a single 64-bit cell to compute the sign. 64 bits is actually quite a lot, and but then I used 128-bit cells, double cells, to check the result. I actually went down the path of working on the double word manipulation. I would need to do all of the precision for 128-bit, but sadly, I think my brain was fried enough that I wasn't able to construct a sort of a D*/, which out of standard words, which is what I was working towards. I suspect with a little more thought that could be done, but I didn't get there. So for the reference table, largely because I flubbed Bill's apparent change in instructions, I did only 11 values. And since these two are just based on sine of, I did 36-degree increments. So because they were, there's actually only 2 unique signs there, and everything else can be sort of derived. So I bake in those constants. And as you can see, 128 bits these days with a 64-bit fourth is quite a lot of bits. These are, to be clear, notice that these values with decimal points are not floats. They're this is using G-fourths, so it will implicitly assume that if you put in a decimal point, but you don't put an E in there, that you're referring to a double cell. And so it's treating these as really what you do is you just ignore the decimal point and treat it as one gigantic number. And there really are that many bits of precision in a 128-bit value. So I got these out of from Wolfram Alpha, which had actually even more digits than it would give you. And then I build up a table and then can index that table on its own. So that's the reference values. And then I'll need some constants to work with here. I've got, a 1 of the same number of positions and a definition of pi. And with that, I can, with the pi, I can build up my degrees to radians with that many digits. And then the key thing that I need to start things off is I need 3 values. So I need in single precision, I need a 1 value, and that meant, a large number, but not as large as that number of decimal digits. And then I need the sine of 1 degree and the cosine of 1 degree. And then from that, I can build up an operation that will do a fixed point multiply by the sine of 1 degree and then by the cosine. And then using that identity that I mentioned before, the meat of the whole thing is in the sine step. And so I can basically take the old sine and cosine, do some multiplies and some adds and subtracts, and get from that the value of the next degree up. And then I can use that to fill out a table of 180 entries, which I can then use to look up the sign of any decimal, or sorry, any integer number of degrees. I even do the mod so it supports wraparound, and then that will give me my sign value. I then have a bunch of helper words to do some printed formatting of these numbers with some number of digits, so I can show off all the digits. And then I build up a printout for each row in various columns based on the item to be produced. I have some additional helper words to print out dashes and to center the headings, so I didn't have to do that manually. And then I then have sort of 2 pieces, a split, which is just the dividing lines between it, and then I print out the column headings, print out the split, and then print out the table with the 11, what I thought were the 11 values that Bill was looking for, and run that to do it, and this is the output. And so I get, obviously lots of bits of precision for the degrees to radians, because that's just being done directly. The top item in each of these rows is the reference value that came from Wolfram Alpha, and then the value below it is the value that I get from my single cell precision sign computation, and then the difference is shown on the right. That's it. Are there questions?
As a linkage here, I'll point out that when I put out the initial challenge, I was working on a decimal friendly output. So we're doing 16 rows or 10 rows, incrementing by 36 degrees for each row. Then I realized the second part of the challenge is going to be doing interpolation. And so we need to be at values of multiples of 4. We need 90 degrees, 180, 270, and 360. So I threw a curve in there and changed the definition midstream. So Brad certainly complied with the initial system, which was based on 36 degree increments rather than 22.5. So back to Brad. Any other questions or comments?
Yeah, well, so hopefully I'll be able to generalize that when round 2 comes. This same method would work for smaller steps. There's a related method. I think it's called Cordic or something, where you sort of make the computation more efficient and you build up only a table of the powers of 2 increments and then assemble those. But that one's more complex. This is the sort of dumb, let me build a table in memory for whatever degree increment your heart content. So although I suspect that the other issue you would run into if you had a large enough table, eventually, because you're clipping off some of the bits of accuracy at the end of things, you would run into issues where the later elements in the table would fall out of line. So back to you, Bill.
Okay. Any other comments on Brad? I'll also want to point out that the implicit goal in here is to have a physical table written into memory rather than just a report, because next time we'll be doing interpolation from that table. So next up, we have Dr. Ting. Come on aboard. Oh, Dr. Ting, you're muted. You're muted.
Am I okay now?
Ah, good restart. Start over, please.
Okay, yeah, all right. Yeah, I really I like the to participate in the challenge because I wanted to check the two E4 system that one I implemented on the JavaScript and the other one on the Java. So you know. One thing about the JavaScript implementation is that JavaScript uses floating point numbers exclusively. There's no integers, okay? Everything's a floating point. So that was very nice. I kind of have to make the transition from integer word to the floating point word. But it is, in the end, it is very satisfactory in that the fourth works perfectly in the floating point word, okay? And it even has all the trigonometry and the transcendental functions built in. So I don't have to really worry about sine or cosine. So here is the, let me see, let me just get you the result. I don't want to pull up the JE fourth. So here is the challenge, okay? And I was thinking that all I have to do is print up the table, and then the table can be saved in text forms. And eventually I could use the spreadsheet to display it, okay? So the first part is to just print the table. And then I just, the challenge is every 22.5 degrees, print out the degree and print out the pi. Pi is also a built-in constant. That's very nice. And then calculate the sine and print it out. So this produces this table, okay? And then I say, well, yeah, you know, the challenge is to really build a table internally. And in the JE fourth, I actually have the array fetch and array store. So you can actually define an array, create an array, and then stuff anything into it, and then read it out with array fetch. Use array store to generate it. And then let me see. Okay, so I have this, you actually have to create the array. Use create n, and then you can stuff it with comma, okay? Just like a regular for system. But the JE4 uses objects, so that you create an object, create a array object, and you use commas to stuff things into its data field. Okay, so this way you build the array, and then it's the M field. So you just go through the table and find the sign and stuff it into the table and fill it. And then it's the M print, which prints out the entries. It's because the sign is a built-in function, so it is the reference itself. So here I only print out the degree, the radiant, and the value, and it's exactly the same as what you will see here. So 0, 0, 0, that's for the degree 0, and 22.5, and you get this thing. Okay. So I think the strange thing is 180 degrees. It is pi itself, and it got a value with a very E minus 16. So it's a very small value, very close to 0. But it is printed out as a very impressive number, but it is just 0. Okay, so and this one actually check out the comma word was not implemented correctly. So this check that out. I said, oh, I didn't get the right number there, and look back into it, the comma was implemented incorrectly. So that helped me debug the JE4 for one more bug there. Okay, so this is JE4 because the floating point is its native numbers. So it handles the decimal point very nicely, and all the numbers gets printed out to its natural width. Okay, the better challenge is for the OOE force. The OOE force in here, I have, it is a 32-bit force. So, and it doesn't have floating point. But in the tutorial, in the lessons, I have one lesson which deal with the sine and cosine. So here is the way to really calculate sine and cosine from the Taylor's expansion. So the Taylor's expansion, I expand about 4 or 5 terms, and it converges quite nicely if the angle is below 45 degrees. And in here, I have the test, and as you can see, the test runs only from between 0 and 90 degrees. So everything worked quite nicely between 0 degrees and 90 degrees. But when I was taking up the challenge and do the calculation, all the numbers above 90 degrees deviates quite significantly. So there's a big bug there, which I didn't realize. You know, the Taylor's expansion assume that the the angle in radiant is a small number compared to 1. If it's bigger than 1, then it diverges. Okay, so the this calculation, my calculation is only valid below 90 degrees. 90 degrees, as you see, it is half of a pi. So it is only about 1.5 in radiant, but it converges. But above 90 degrees, it's getting worse and worse. So I have to correct the calculation of sine by actually limit the calculation within 45 degrees. Okay, so I test if it's less than 45 degrees, then the calculation is correct. If it's bigger than 45 degrees but less than 136 degrees, I would calculate with cosine, but reduce the angle by 90. Okay, and if it is between 175 and 225, I would subtract 180 and use sine to calculate, but the value has to be negated. And so if it is between 226 and 316, then I would subtract 270 and use cosine, but the result has to be negated. And if it is greater than 316, then I have to turn it into a negative number by subtract the 360 and use sine. Sine takes care of this, the negative value very nicely, so you don't have to worry it. So in this way, I limit all calculation to within 45 degrees and got the results very nicely. Okay. And so here, yes, let me see. I have to. One part is to print out the table, and the second part is same thing. Create an array and fill it with the comma. Okay. And here, I calculate the result, and I have to backfill the reference values. Okay, so the numbers, I mean the angles, are all use. The pi is 31,416, and 1.0 is 10,000. So everything has to be scaled that way. And so the 36 degrees is 0.58378. And the 72 degrees is 0.9511. Okay, so here, I think I still have the EE force there, okay? All right, and I can, let me see. Let me just do the printout. So here, and I just print the table. Uh-oh, sorry. I don't know what's going on. Empty stack. Okay, so, let me try the other way. I think it used to work. Paste. Okay, I think there's a bug there. I don't know what happened. But okay, this is not time to do the debugging. Let me just go back to the screen there. It used to work, but I don't know what failed. But this way I can print out a table, and generally it looks like the other one, but without the floating points. And the calculation, actually, the calculation are just exactly these numbers. Okay, so there's no error at all, up to the accuracy of 1 part in 10,000. Okay, Bill, I'm done. Sorry about it. That doesn't work, but it worked last night. Okay. Okay, let me get to the screen back to you. Okay, stop sharing. Okay.
Well, thank you very much. Very good. That's really highly enjoyable because I love the fixed point implementation, which I was hoping somebody would do that. And the fact you have to cope with real life things of the number 1 being 99999, and you have to cope with that. And then of course, we always have to cope with the empty stack report. So you kind of touched all the bases in fourth in that. Do we have any other comments or questions, please?
Yeah, the comment was that I'm working on 36-degree challenge. And last night I looked at the announcement, and the challenge changed to 22.5. Okay, I can do that. Okay, yeah, the degrees has to be integers. Okay, so I say, oh well, I just changed the floating point implementation and not keep the 36-degree challenge. That's it.
This also is very much like Charles Moore. It says, if you don't like the result, change the problem statement. So that's all we did. We changed the problem statement. And Sam, you'll go ahead.
Yeah, I noticed that as Dr. Ting was trying to get his code to run, the first thing that it complained about was that pi was undefined. So I'm sure it probably would have run fine, but it looked like there was a portion of the code that wasn't loaded into the dictionary at the time.
Oh, yes. You are right. Okay. Let me try it, and then I'll grab screen. Thank you very much. It is that the sine and cosine was implemented in my lessons. So I have to load the lesson first and then load the challenge. Okay, I'll try to do that. And you guys go ahead. And when I get the result, I would cut in. Okay, thank you, Samuel.
And that's, again, perfect. Thank you so much, because it's actually neat to be able to do this stuff on the fly. It is really neat. Do we have any other participants before I show mine? Hearing none. This implementation uses the matrix forth that I've been working on, and the kind of a cheatsy aspect of that is that there's so much built in that it simplifies the work quite a bit. So here's the pseudocode that I worked around. First was I created a matrix, 17 rows by 1 column, and then manually entered the reference values from an external source, which you'll mention. I entered the reference values for 22.5 degrees, and this is my check to make sure it's going to come out right. Then I reformed the matrix and added 3 more columns. So now it's 17 by 4. Then I copied the column 0 to column 2, which is our reference. So the reference values are now in column 2. Then calculated the degree values by multiplying by 22.5 into column 0. From that degree values, I computed the radian values into column 1, and then finally computed the sine values into column 3. And how do we get the reference values? Well, I just reached over into my ancient file of fine old souvenirs and brought out my college slide rule from 40 years ago, and my post log decittrig slide rule. Then I got the values for sine. So in this case, now we're using the matrix fourth. We're going to do a circle with 16 divisions. I create the table with 16 plus 1 rows. That's the table in green. Then for the table, the following center gives, center portion gives the values from 0 to 360. These are 17 entries that are literal values that are entered. Then as a quick check, we do a list. So the list command works on table, and it brings out to 4 decimal places the values that were entered manually. Again, the slide rule values. These are all done in 64-bit fourth, 64-bit floating point. And here's the copy. We take the table 1, and now we resize it. We we expanded it from 1 column to 4, and then copy the second row is to copy the column to column. So we go table column 0, then we say table column 2, and then do a CC copy, which is column to column copy. And you see the arrows pointed out that the columns have copied across. Now here's how we complete the table. We've got the degree values in the first column. So we set up the do loop range, and then the table with the little bracket I 0 bracket, which gets the storage address that we're going to store into. The next one pulls the value of sine and does the division by into 16 brackets or 16 buckets. And this is calculating the sine numbers with a 22.5 degree increment. The second blue line computes the radians. Then the table bracket I0 stores radians. That value is duplicated and saved. The resident sine function calculates the sine and stores that. So we complete the entire project in essentially one screen or one command. The generic report accepts the default column width and the default number of decimals. So in this case, we're doing a default width, I believe, of about 12 characters, and the decimals, I believe, is 4 or 5. So coupling that table to report, here's our output. The angles run from 0 to 360, 2 decimal resolution, the radians 0 to 2 pi. The sine, of course, from 0 to 0 with the reference values. Remember, these are from slide rule, and then the computed sine values. So next month, those of you participating in this, you can regenerate your own value of tables. And when we've seen table, I mean, not report, but I mean a physical table in memory. And then we're going to interpolate so that you just input a single value in degrees and then scan through the table and pull out the radian value and the sine value. It's a simple exercise in how to generate tables, how to fulfill the information of the tables, and then how to make use of it. And again, the credits go to Andrew McEwen and Tom Zimmer for 132 fourth and the European fourth team who updated it. This information is saved at GitHub, and it'll also be at the Silicon Valley Fourth website as a PDF. And do we have any questions before we go back to Dr. Ting?
Yeah, I got it working. Okay.
Good work, Dr. Ting. A very quick recovery.
Before we go into Dr. Ting, I just wanted to point out, Bill, that I was in the last class of engineers at Iowa State University that learned the slide rule. We spent most of the semester on the slide rule and like 1 week on the calculator, and the next semester it was the opposite. So I have fond memories of slide rules.
Being historically oriented, being this old, it it kind of warms my heart. I'll add another comment to that. I graduated in 62, worked 10 years, 9 years, and it was all slide rule work. And then started my own company in 71. And we began to do active filter work. And the calculations for doing active filters were fairly extensive. And after some hours and days frustrating, we had a customer come in the door who wanted a major project done. We went out for lunch to Sizzler, and I said, I'll be glad to take on your project. I need a retainer of $1,000. And they said, okay. So we signed an agreement on the back of a Sizzler menu, and they sent me a check for $1,000. And then I went out and I bought the HP programmable calculator for $1,000. And that was the one that used magnetic cards in it. And I was able then to program my active filter designs into the magnetic card. And so for the next roughly 3 years or so, I ran my company on the HP 65 calculator. And then finally we got an Apple II, and we got the spreadsheet program for it. Anyway, I'll say back to Dr. Ting.
All right. Okay, let me just go grab the screen first. Okay, here is the screen that which actually worked. But let me close this one and start over. Okay. So here I have the object-oriented E4, and I just press this run, and I should get the win. Yeah, I should have the window there. Okay, so here the first demo is the words. So we have all the words, and then I have to load the lessons first, okay? Because the lessons have the sine and cosine calculation in it. I would copy it and go to here and paste. So here you see the sine and cosine calculation is right here. Okay, so I just hit return, and everything's get compiled. And okay, now I can load the challenge. Where is the challenge? Okay, the challenge is here. And the first part of challenge is to print out the table. Okay, print out a table. All right, you can see. Oh, sorry. You can see the numbers. There's no reference number. It's just a calculated number, okay? And now I load the second part of my, Okay, here, copy, over here, paste. You can see the first part is to fill an array, okay? And now I create the array, filled it, and this is the M reference, just fill in the reference values and do it, and then print out the contents, okay? So if I just hit return, and I get a table, and you can see the calculation agrees perfectly with the reference, and that's the result. Okay.
Beautiful, beautiful.
Yeah. Now back to you. Okay. Thank you. Thank you, Bill, for the challenge. And it actually shows the bug in my sine cosine calculation. I can get a chance to correct it. Okay. Thanks.
Thank you. Very rewarding, absolutely rewarding. Thank you. Quick recovery. Thank you, Samuel, for a tip. We all did our part. And so we'll turn it back to our fearless leader, Kevin. And next month, those of you who were quiet on this session, come in next month, generate your table, and then give us a way to interpolate and pull out degrees from your table. And of course, remember, we're only having values at 45-degree intervals, so you need to interpolate in between, and you get to pick your own method of interpolation. Thank you, and back to Kevin.
Yeah,
Thank you,
think,
Bill. Go
I
ahead.
think I will build my table with the 15 degrees interval. Okay. Thank you.
I'm not sure if Bill is remembering the Bullwinkle and Rocky cartoons of a bygone era when he calls me the fearless leader. I'm certainly fraught with fear. And as far as leader goes, well, let's not get into that. But thank you, Bill. And thank you for the challenge and the presentation. Thank you, our presenters. I'm very grateful. I'm very grateful that you come up with this stuff. Perhaps less so that it comes as I'm trying to get to bed after posting the agenda meetup. Just when I thought it was a ghost town agenda-wise. Our esteemed colleagues, some of our esteemed colleagues saved me from disgrace. So thank you. We'll hope to see you guys next month. Maybe start thinking about fourth day. I think that fourth day will be a Zoom meeting. It's too many moving parts to do it in person. If Stanford is in a position to accommodate us, we may have a viewing party and maybe some prisoners that are actually present on the Stanford campus at that time. But I wouldn't set my on it. It may just be entirely Zoom on like last fourth day. So thank you all, and continue to talk among yourselves, and let's plug on the recording at this time.